Well, good afternoon, everybody. My name is Jorge Salas, and I'm just going to make a very short introduction about what is Sener, what we do, because, well, probably not so many people know about Sener here in the UK. So I'm part of the geotechnical and tunnel team here in the UK. We are around 30 people in the London office. So yeah, as Arabel was explaining before, I have been involved in the past in HS2, previously working with the Strabag and making project related with segmental lining design and ATM and many others. But the important person here this evening is Alfonso. He has around 13 years of experience, and well, he's going to present the Outfall Tunnel. So probably, as I said, like not many people know about Sener, but do you know that the Sener designed the retractable pit system in Bernabeu? So this is like an idea that came from us, from Sener, and we presented that idea to Real Madrid, and they thought that it was probably a very good idea, and they implemented. So we were the ones who designed or made the preliminary design, detailed design for both the civil works, but also everything related with MEP, architecture, ventilation, systems. So you may think that maybe this is something that it has nothing to do with the underground works, but this system is kind of dividing the pits into different trays that are moved by an automated mechanism that takes these trays into an underground chamber that is called hypogead, and this is the name of the system. So this is something that Sener developed or came with this idea, and this is the kind of project, for example, that we made in Sener. So not only typical civil projects. So another project that we were involved, it was the Stonehenge tunnel project. So we were the preferred bidders. We were a part of the DJB that it was comprised by Atkins and Jacobs, and well, I think probably everybody knows that the project was cancelled, but well, at least we had the opportunity to participate during the tender project, and we were awarded with the project. Okay, so now I'm going to present some figures about the company and what are the underground capabilities that we have. So the company was founded in 1956. It was originally founded as a naval engineering technical office in Bilbao, in the north of Spain. At the moment, we have it was in figures from 2023. We had order book of around 1.3 billion, and we have around a workforce of more than 4,000 people in different offices around the world. And around 64% of the people, they hold a master's degree. So that shows like the degree of specialization of the people that are working in the company. And even though that we are a Spanish company, the Spanish sales are not the main important part of our business. So yeah, the non-Spanish sales are around 83%. We are divided into different business units. So we have the aerospace business unit. We have the mobility, that is where the geotechnical team and the terrain team is placed. We also have the energy business unit and the advanced facilities. So well, probably everybody understands that the aerospace and defense, we develop like some kind of technology for space mission satellite systems, defense applications. And the mobility is where we are, and we are focused on transport infrastructure, railways, metros, ports, and etc. And the energy business, they are involved in power generation and oil and gas projects, but also more new things like hydrogen generation and this kind of projects. And just recently we acquired one company that is called Quark, and they are developing data centers and the design of these data centers. So this advanced facility unit, they deal with this kind of projects. And additionally, we make like semiconductors facilities and many other projects of this. So yeah, this is the way that the business units are divided within Sener. So in terms of the workforce, we are, as I said, like more than 4,000 people. So mainly the main part is based in Spain and in Europe. So in Spain we have around 2,500 people divided in the offices in Madrid, Bilbao, Barcelona. We have also like a very important office in Mexico, and we have also many other important offices as the one in Australia, where we bought another company that is called Tactics. So now we have around 200 people there, and also we have some other offices as the one in Brazil, or we have now a very big office in Canada where we are working quite extensively. So yeah, if we focus on the business unit of mobility, that is where Alfonso and myself where we're working. Along all these years from the 50s, we have been developing many kind of rail projects, around 15,000 kilometers of rail. A lot of them is high-speed rail. Also, different projects related with transit, metros, light metro, highways around 20,000 kilometers. Many projects in ports. It's also like a strong discipline within the business unit, and many other water, airports. Okay, so if we focus on tunnels, so we have been developing projects and which are summing up around 1,400 kilometers of tunnels. So we have been working in different type of projects as DBM, microtunnel, cut and cover, and ATM projects. And well, the application is in road projects, railway, subway, hydraulics, and many others. Okay. So this is an example of the capabilities that we have in terms of numerical modeling. So we work a lot in Flat 3D, and this is our main tool, I will say, for numerical modeling in 3D. And this is an example, for example, in the bottom part and at the right-hand side about ventilation tunnel for the Bernabeu Stadium project. But well, here are many other examples of Guadalajara Metro where we develop an underpass issue. So yeah, we develop some numerical models there. And also, for example, another example is the hydroelectric power plant and underground cover on the left-hand side at the bottom. Okay, so in our way of working, we are starting to implement integrated processes where we try to be involved in from the beginning. For example, from the beginning of the project, we start with everything related with the geology and the interpretation and modeling in 3D with, for example, with leapfrog. This is an example, for example, of one pump storage hydro project that we are developing at the moment. So this is just an example where we started with the geological and 3D modeling in leapfrog. Then we go to how to approach the geometrical design, and we develop the design with tools as Rhinoceros. We also are using other tools as Grasshopper to try to automatize processes and to make parametric design. So from that, once that we have the geometrical solution and the geometrical design, we go into different directions. We apply that into BIM. That is, and especially in this project, that it was a very high standard requirement. So we developed the let's say the design in BIM, and in the other branch of the application, we develop numerical modeling from that one. So this is an example of how we, from the design that we implemented in Rhinoceros, Grasshopper, then we make the mesh in tools like Riddle, and then we are making the numerical model, for example, in Flat 3D. So this is, for example, an automated process and the way that we tackle this problem in this project, for example. So I'm going to present like some important projects that we have been developing in the last year. So we are working in many regions around the globe. So for example, this is one of the latest projects. This is the Coast Harbour in Australia. Yeah, this is a 3 tunnel project with a total length of 900 meters, and we had like very wide sections of the tunnel. We were also developing the all the design, the civil works, and also everything related with the internal structures, ventilation, and so on. For some reason, lately we have been involved in many projects that involve design of tunnels underneath water bodies. So this is an example of the tunnel under the Suez Canal. So yeah, that was a project where we have many challenges, and we've developed the segmental lining design. We also have to implement the design for ground freezing for the cross passages. And well, as you see, we were also designing the launching and receiving shaft, this caterpillar shaft. And additionally, apart from the civil structures, we were doing the design of power supplies, station, lighting, ventilation, and many other disciplines. So this is another example where we are involved. So this is the project in Panama, in South America, Metro Line 3. So this is a design joint venture with AECOM, where they are, in this case, developing the design for the segmental lining, and we're involved in the design of everything related with geology, geotech, and the design of some stations as well, and everything related with MEP architecture. I mean, we're involved in many disciplines within the project. Well, that was definitely a challenging project. We had to do, for example, a lot of geophysical interpretation under the canal because of the difficulties to make drillings on the canal. So well, that is one example of, or another example of project with involving tunnels under water bodies. So this is one of the latest one that we are involved, and this is the Scarborough Subway project in Toronto, in Canada. So we were involved from the beginning in the system part of this project, but at some point of the project we took over from a different designer. So we're doing now both the systems and the civil parts until implementation. So this is an example of where we are involved in the connections with the main tunnel, and this is an example of an overpass solution and all the models that we're preparing for the segmental lining and the intersection with the emergency exit gallery. And the latest project that I'm presenting today, this is one of the most challenging projects that we are involved at the moment. So this is the pump hydroelectric power plant project in the Canary Island. This is called Chira Soria. So this is a very large project involving 2 very large caverns with approximate dimensions of 31 meter height, 18 meters width, and around 160 meter length. So additionally, we develop all the design of approximately 6.5 kilometers of tunnels, 4 main shafts, and yeah, so this is a very challenging project, and well, we are applying like different workflows to optimize the design because it's quite challenging. Okay, so I think that's everything from my side. So now I'm going to hand over to Alfonso. Thank you.
Well, good evening, everyone. Now that you know Sener a bit more, let's focus on the case study that we're going to present here today in this lecture. This is the Los Angeles Outfall project. We are going to focus on the lining designs that we did for that project, which was quite challenging for us. So the project, just a brief review. This is a sewer tunnel that connects an existing treatment plant and connected to the existing outfalls. At the moment, there exist two tunnels. We were built between 1937 and 1952, which are very old, and they had not been revised since built. And this project, the main objective is just to replace the existing buildings with a new system in order to last for another 100 years. As I said, this project is a major infrastructure in the Los Angeles County, and as I said, we want to highlight the different challenges that we have to tackle regarding to the segmental lining design, and also from the constructive point of view, what are the optimizations that we propose for this project. As Arabella was saying, this tunnel has a length of a bit more than 11 kilometers. The internal diameter of the tunnel is 5.5 meters, which just to say this is a TBM tunnel. And the main thing is just to increase the capability of discharge capacity of the current systems. What we are going to do, as I said, is in order to replace the oldest tunnels, this project came up, and the target is try to send water already treatment to the oceans with a maximum capacity of discharge of 2.5 million cubic meters per day. Regarding to the geology of this project, as you can see here, this is a longitudinal profile of the tunnel. On the right side is the last part near the ocean. Sorry. As you can see here, it's very different depending on the area that we are encountering. So the geology was divided in 6 ridges. The first 3 ridges, the 1, 2, 3, are the ones with less overburden, around 30 meters, and because of this small overburden and the fact that this tunnel, as you can see here, is going upwards into the ocean side, is going to be in pressure when entering in operation. So this part was with very shallow cover and with a very low water pressure externally. Then we enter in a intermediate section, which is the ridges 4, which is a difference between the first part and the second part. This is a transition zone where the rock material was not so good as we thought, and because of that, a different alignment was proposed for that part of the line, and then the rest of the tunnel, the ridges 5 and 6, are the one with higher overburden, up to 143 meters. And the thing especially in this area is that also the groundwater level was about 90 meters over the tunnel alignment. So as you can see here, the tunnel has 2 very different geotechnical perspectives, the first part and the second part. Also, we want to highlight that in this project, as we are in Los Angeles, the project crosses different faults. The most important ones are the Palos Verdes and Cabrillos faults. Here in this plan view, we can see where they are located. These are the branches of the faults zones, but this is only a preliminary study, and the risk of having additional faults along the alignment was higher. So these are the main ones, but the risk of having fault materials along the alignment was almost from the beginning until the end. As I said, the maximum water pressure that we need to handle in this project is 9 bars, and for that reason, for these 2 types of geology, we need to design the lining for these variable situations. Just to give you a history point here, these are some photos of the previous tunnels that we are going to replace with this new tunnel. And in the left figure or image, we can see that they have some geotechnical issues. You can see here how they encounter squeezing materials. You can see how the section is reduced in that photo. And also in the right side, there is another picture of the same tunnel having also a risk of watering, but the main thing here is that they have like an uneven squeezing. As you can see, the red part of the tunnel is moving inwards, and instead of having the horseshoe shape, it's almost like a vertical right side. As I said, these tunnels come from are very old. They experience squeezings. The good thing of these tunnels, different from the one that we are designing here, is that they were built using NATM method, which is very beneficial for this kind of situation when you have to deal with squeezing grounds. Here, this is an advantage because when you are doing a TBM tunnel, and in this case, you need to estimate that potential swelling as better as possible in order to avoid issues, because that lining is more rigid and you don't have any other opportunity. If there is a mistake, you will regret it. In this case, you can re-excavate and rebuild the shape of the tunnel without any problems. As you can see, these tunnels were built, filled with water, and no one has been revised it. So we don't know how they are, and that's why they need a replacement. So the new project, as I said, it will be a TBM tunnel. Focusing on the lining design, in order to try to get one design for the whole tunnel, we ended up having 3 different types. For the first part of the tunnel, the one with the lower overburden, we propose a segmental lining only using steel fibers and with a concrete compression strength of 40 megapascals. These measures are in US measure, which correspond to 6,000 psi. The main point of this lining is that as there is very low overburden and this tunnel will be in pressure, we need to propose this lining with a post-tensioning system in order to withstand this internal pressure, in order to try to maintain in any situation in full compression. For the second part of the tunnel, the one with higher overburden or risk of swelling, as we saw in the existing tunnels, we propose a standard segmental lining with rebar reinforcement, but with higher compressible strength of the concrete, up to 8,000 psi, which corresponds to almost 55 megapascals. The reason of this segment is just in order to withstand all the high squeezing forces that are expected in this part of the tunnel, and also try to be able to withstand also the TBM forces when apply the truss on the segments, especially in the areas with higher overburden and squeezing risk. And a third type of lining came up because, as we saw in the geotechnical profile, there is a transition zone that is not as demanding for the stresses as the second type, and it has enough overburden to avoid to have this post-tensioning system I told for the first lining. So we came up with a third type of lining, which is the same as type 1, but with the necessity of using a post-tensioning system. At the end, the distribution of the segments along the alignment came, as I said, first type for the first part, then a transition with the type 3, move on to the second type for the higher overburden, and at the end, near the ocean, where the overburden reduced, we need again a lining with post-tensioning system. Just to highlight that for this first type of lining is the first time we are using a design of post-tensioning segmental lining in US. Is the second in the world, but in this case is the largest installation because of the length of this type of lining that we are going to install in this tunnel. Getting into details for the post-tensioning system, we want to show you what was in the reference design. As you can see, there is very small details. You can see the different layout of the ducts and the pockets in order to do the post-tensioning. And with that small information that we had at the beginning, we try to optimize it, and we propose what you can see below. The main changes that we did, and we want to highlight, we changed, as we will see later, the original ducts for the PT system was rounded, and we changed it to flat distribution in order to avoid any crossing of the strands, in order to facilitate the tensioning. Also, as you can see near the PT blocks in the segments, there are some curves, very large curves. So we try to avoid that in order to reduce the losses when stressing, and also to avoid any tensions inside the body of the segments because of these curves when doing the post tensioning. Also, in order to be able to have a strain layout of the PT, instead of having curves and avoid that, we try to adjust the distance between the radial bolts in order to achieve that and avoid any curves on the PT. Here in the right side, sorry, because the contrast is not giving us very well detailing. So here are the PT pockets when you do the tensioning, and here is how it's proposed. The strands are in the middle of the segments, embedded, and we use a monojack in order to strengthen one by one the strands for the PT. Also, we want to highlight all the different numerical modeling that we have to do in order to get some results for the design we want to have. Here it was very challenging, so we try to do a specific model for the segment that has the PT pockets, which is the critical one. So we try to measure the different forces that it will be applied on the segments. The main ones are the torque forces, because the TBM pads are very close to the PT pockets, and we need to know if there is any bursting forces that exceed the capacities of these segments. Also, we want to focus on the joints between the segments, as you can see in the left part at the bottom, in order to also try to estimate the bursting forces that appears because of these joints. We did all this analysis because our main goal here was try to achieve a lining without traditional rebar. Try to do it with only steel fibers. And also the other area that was critical was the area between the PT pockets. So we try to modelize the post-tensioning forces applied on this surface in order to see what are the additional compression that we have in this part of the segment, and be compatible with the overall forces that we have for the ring itself. We can see here in the picture some of the details that I was explaining before. Here's the PT pocket when the cables came in, and at the point when we are strengthening, and at the bottom we can see the details of these PT pockets and what the minimum reinforcement. This is the only reinforcement that this segment has. The rest are only fibers, but for this specific area, when we are stretching and tensioning the strands, we need that surrounded rebar in order to handle all these potential tensions that it can appear in this part of the segment. As I said, the main objective of this PT system was try to provide enough compression for the segmental lining during services, as the tunnel will be in pressure. The main objective, I said, the tunnel try to expand because of this internal pressure. There is not surrounding pressure from the external water and the ground itself. So we put this PT system in order to provide additional hook forces and try to ensure that everything works in compression, and there's no issue with the gasket performance, and try to prevent any infiltration from inwards or outwards. As I said, we changed the flag geometry to have a flat ducts, as you can see in the bottom image, in order to minimize the losses. Also, another thing we we propose is use unbound strands. So in this case, each strand is encased in plastic shield. So that gives us additional durability because it protects against corrosion, and also allow us to do the tensioning one by one. And the third detail of this post-tensioner system is how we handle the connections between the segments for the same ring. So in the joints, we need to propose different accessories in order to assure that there is enough water tightness, and in order to prevent any material to get into the system, just the grout when we are installing the segments, or any water or anything that may enter in the PT systems that doesn't allow us to do the work and get in the cables. So here are some of the details of these joints. As I was saying, in one of the faces we installed this O-ring, which is this shape, like it's an EPDM material that's that it's around the trumpet. And on the other side of the joint, we installed these Teflon plates in order that when the segment gets in contact and we apply compression, this joint is sealed and no material can get into the PT system. Here we try to show you, this is something that normally we only focus on the numerical modeling and all the permanent situations, but here what we are trying to show you is all the different stages of the production or the fabrication of the segments, and also it's important to check this transient situation, all the stacking, the transportation, and how it's installed. Here we can see a video when we can see how they put the gasket, all the PT, pour the concrete, and how they prepare the segments for this project. This image are from this project. As you will see, all the details of the PT when they are demolding these segments, we can see all the PT and the joints. So this is just a reminder for us that we only focus on the permanent situation, but we need to pay attention how to deal with this transient situation, because as you can see here, when the segments are with very low concrete strength, they were piled in 3 in the factory, and here at the end, when this is an on-site view, they piled all the segments for one ring, one on top of each other, the 6 of them. Now, regarding to the PT, the original design proposed 4 strands and 2 ducts per ring, independently of the point that you were encountering the need of PT. So we try to optimize it. So we analyze 4 different configurations. We always stick to maintain 2 tendons per ring, but we analyze 4 different configurations of strands. So 2 tendons with 4 strands per each, 3, 2, and 1. Here in this table we can see the hook forces that we put in the aligning because of this PT. We measure it on the PT pockets, which are the ones because of the losses and how you strengthen the jacks are the points with more losses, and the minimum value of the PTs in these points. And also we focus on what's the hook forces that we gain with this PT in the closest joint. So with these figures, we try to do this joint dilation analysis, which is try to estimate without the PT. We know the internal pressure that we have along the alignment for different points, the different type of ground that we have, and try to see with the external pressure and the internal pressure of the water how much the ring may increase, may get into tension. So the objective here, what we try to do is try to do this analysis and see what's the opening that we have in each joint without PT, and try to implement as much PT in order to make sure that the gasket, which is here, the gasket criteria, this is with an offset of 10. All the points along the alignment are within this envelope. So with this exercise, in order to see what's the minimum PT that we need to provide along the alignment in order to satisfy the gasket criteria for the different points, we came up with this distribution. So you can see again the geotechnical profile for the first part of the tunnel with a small cover and very low groundwater level. We ended up with 3 strands. Then in the middle part we have to increase to 4 because of the external water was even less and the material was a bit worse than on the first part. Then we switch again to 3 strands. When we are increasing the groundwater level and the overburden, we could optimize it to 2 strands per tendon. And in the area with a high overburden, as we said, no PT is required. At the end, near the ocean, we ended up with having to use the configuration of 2 strands per tendon. In total, just to give you an idea, this project has consumed about 530 kilometers of cables were installed in this project. Now, I want to highlight another issue, another thing that it was risky, and we tried to propose a solution, which was how to assure the stability of the key segments when high confinement pressure is applied on the ring. So when you are building a ring near the TBM, there is a point where you retract the jacks, and that segments, the only restraint elements are the bolts that we have or the dowels and so on. But here, with this high overburden and this external pressure, the risk of having the case segment to move and jump from their position, it was quite risky. So we tried to propose different chains to optimize and minimize this issue. The first one is what is shown here. We try to reduce as much as possible the screw angle of these segments, and we propose 8 degrees, which is the minimum we could achieve in order to reduce as much as possible the tangential forces, but also try to be compatible with the TBM, with the maximum length that the TBM jacks can retract. The other thing that we propose here to restrain the key segment was to install a different voltage system and try to bolt this case segment to the previous ring. So this gave us additional restraint forces to avoid this issue. And at the end, with all these things, the change of angle and try to use this voltage system with the previous ring was enough to provide enough friction or restraint. But in order to have an extra safety on site, they propose to use what you can see here is just a system that also restrain the case segments with the previous ring. Try to connect in the share key. So they connect the share key, they block it, and this is an extra safety measure to avoid any movement of the key when the jacks are retraced. Now, from the construction point of view, we also propose different optimization. The first one, as we saw, there are very different segment types, and we have to propose a vacuum erector which is compatible with all configuration. The special one is the segmental lining one with the PT pockets are the critical one. So we try to adapt this proposed different foam pieces in order to assure the vacuum forces are applied correctly for the different segmental lining. Other optimization that we did is in order to do the post tensioning. It was planned to do it after the TBM, but we thought that it was beneficial just to install 3 specific gantries along the backup in order to do the work in parallel with the tunnel excavation. So at the end, the backup ended up with almost 200 meters, which the normal one is 100, 120, because they implement additional gantries in order to be able to do all the pump stationing works. Meanwhile, the TBM continue the excavation. As you can see here, these are some photos of these works. The TBM is still ongoing, and in the meantime, some workers are installing in the PT using these gantries. Other important thing that we propose here for the PT, in the specification they said that you need to do some drillings in order to make sure that when you, because that system was filled with grout in order to provide additional durability, they propose to do some drillings, drilling holes in order to inject the grout, and when you feel you see the materials getting out of these holes, you know that the system is full. So instead of doing that and damage the segments, they propose to use a vacuum grouting, which is from one end of the pocket. They provide a vacuum system all around the PT ducts, and from the other point they inject the grout with a very low pressure. So with this system they make sure that there was no air bubble in the tunnel, and it remains fully grouted. The third point that we want to highlight from the construction point of view, we propose one segmental type because this is a universal ring, but the contractor says it would be beneficial to have two different type ring for the type 1. Same configuration, everything the same, but the difference are here, that in one case the PT pockets are located in two segments, AB, and in the additional ring type it was on two different segments. The aim of this having these two type of segments for the PT is just to avoid that, according to the alignment, none of the pockets remain in the bottom part of the tunnel, because it was impossible in that case to put the cable in. So with this configuration, we always have the pockets in an accessible point to install the PT. And the last optimization we did for the construction point of view, it was just to adapt the TBM, the truss path, because of the squeezing risk, the TBM was designed to provide a maximum truss force of 158 meganewton, which is quite a lot for the size of this TBM. So we ended up designing the segments to withstand a maximum truss forces of 82 with the standard path, but in case of the TBM get stuck and we need to apply all the forces, all the maximum forces, they propose to use an enlarged parts, which provide more contact area between the segment and the TBM path, which allow us to increase the truss forces without damaging the segmental lining. So just to finalize, we want to highlight summarize some key points. At the end of this project, as I said, we ended up having designed 3 different types of segments, one with the PT and steel fibers, one steel fibers alone, and also another one, the type 2, with traditional rebar and high strength concrete. As I said, this is the first tunnel in the US that has this post-tensioning system installed, and the largest worldwide, with the length of post-tensioning system longest worldwide. As I said, the number of PT cables are over half a million meters, and the success of this project is thanks to the contribution working as one team, Dragados, which was the contractor, Sener, which was the segmental lining designer, and the county and the property, which gave us the opportunity to optimize this without compromising the project specifications. Just to finalize this presentation, some lessons learned that we want to share with you. Firstly, is that a complete geotechnical survey is mandatory to do in this kind of complex geological works, because for the budget of these tunnels, any deviation could be very related to this geotechnical complexity. As a good rule, it's better try to spend a bit of more money in the borehole and the campaign in order to increase the information as much as possible, in order to avoid any additional or extra cost because of the knowledge of the geology that you are going to encounter, especially in this type of tunnels, so almost 11 kilometers long and with only 1 TBM, and having all the history of the previous tunnel that we had. Also, we want to highlight that for the squeezing effect, it's very important to do a specific geological campaign in order to try to not to use only, because for example in this project the specification tells you what's the effect of squeezing that you need to apply with some random numbers, and there is not back information how they came up with those values. So a specific geotechnical campaign to try to estimate the squeezing effect and the potential load, how this is going to affect in the long term, it's very important to do it. And finally, some lesson learned from the post-tensioning system is that it was very useful to do a trial test of the PT before starting the construction of the tunnel, because with that mock test we ended up with this construction optimization. It's better to install these gantries, try to do it simultaneously with the excavation to not increase the program of the tunnel. So at the end, this mock-up was very useful to learn how to install this PT system, because it was new for all of us. Try to get some advantages and try to propose as smooth as easy process to get installed into the tunnel. So that's all from my part. I hope you like it, and thank you for listening.
Thank you. Can anyone help me with the mics? Solo? Do you have any questions?
Thank you for your presentation. You mentioned you have launched a special geological campaign to estimate the squeezing force. May I know how, some details about how it is estimated, and how do you consider it in the design?
Yeah, well, as I said, in the project specifications, they told us what was the squeezing effect load that we need to apply in the Segmental line. Just to give you an idea, it was not other option. They said that according to the overburden that we had, you need to apply 10 times the diameter of the tunnel vertically and 12 times the tunnel diameter as a hook forces in the model. We tried to see if that was realistic or not. We didn't have enough information. That's why we said that the having an additional geotechnical campaign specifically to address the squeezing is very useful, because at the end the specification said this is what you need to do, and we don't know what happened if this value are exceeded. We also take into account the safety factor for the loads and everything, but at the end, if you don't know perfectly how the squeezing is going to happen and try to measure it, and with a TBM tunnel as it is this case, any error trying to figure out what are the loads, it's going to be very difficult to solve if that happens. If the squeezing forces are higher than you are expecting, for example, what you want to do? And this is for a TBM tunnel, because for the older tunnel, well, they encountered this. They were different conditions, but at the end, when you are doing a SEM excavation, you can allow the ground to relax as much as you can. You leave it for a while, you put a flexible lining, you allow the ground to deformate, to squeeze, and when it stops, you say, okay, I need, the section have been reduced 30%, no problem. I re-excavate and put the shape that I need, and you know that the surrounding material has been squeezed and is not going to move more. Here in a TBM tunnel, we use this approach, but let's see, because at the moment the tunnel has not finished yet, and as we saw at the beginning, there are a Cabrillo fault, which is the riskiest one regarding to the squeezing. So let's see what happened there. At the end, this is what has been designed for this load I told you, 10 times the diameter vertically, 12 times horizontally, and let's see if that's enough to handle the stresses for the squeezing. If not, we will see if we need additional rest. I hope no.
Yeah,
Thank you.
There is one at the back. Thank you.
Great presentation, thank you. Did you consider any tendon relaxation for the long term? And
For the PT?
Yes.
Yes, we take all when we design the PT, we take into account all the different deformations, the elastic ones at the beginning, and also when you have a steel in tension, the long term, you have that tension, they get well, it get elongated and the stress is reduced. So we took both things. The instant ones, when you are applying the tension and you stop it and you block it, yeah, in that point you have some losses, and because of having a steel in tension for a long time, you take the second order of magnitude for these loads in order to take into account and use the minimum force, taking into account of all these losses.
Approximately what percentage have you considered for the
instantaneously? I will tell you, it was like 15%, and the long term it was about 7%, depending on how much stress you put. At the end, as a safety measure, in the contract says that you cannot strengthen the strands more than 80% of the elastic value in order to avoid any issues. But even with those, these are the percentage of losses compared with the maximum and the theoretical one when you stretch to the 80%.
Perfect, thank you. Just one last question. Did you position the PT at the centroid of the segment?
No, it's not at the center, because at that point we want to move it a little bit on the extrudos, just to increase the thickness internally in order to avoid any spalling issue that you can see because of that.
Thank you.
Yes, there is one online first. So Daniel de la Rosa, thank you, Alfonso and Jorge, great presentation. When it comes to numerical modeling, what would you say was the biggest challenge you faced?
Well, the biggest challenge it was how to design these PT pockets, because we wanted, as I said in the presentation, try to reduce any curves, so we need to place it a bit more close than we want to the edge of the segment, and in order to make sure that the stresses and the loads that are going to be applied on that part of the segment, we ended up having to do this 3D modeling just to make sure that these segments only with steel fibers can handle these bursting forces that may appear when you apply concentrated loads.
Thank you. There is one here. Hi.
Yeah, thank you for your presentation. Regarding the previous question on long-term behavior, was there any interesting thinking on monitoring and instrumentation, perhaps putting load cells for long-term behavior and monitoring?
For the PT, you mean?
Yes.
It was not possible. So at the end, what the contractor did is we know how much, because at the end the contractor only knows how much do I have to elongation of the cables to provide the load that you are giving me from the design point of view. So at the end, they ended up only having this, and because of the durability of this system, as soon as they ended up with tension in this cable, they put a cap and they do this grout. So at the end, that system gets like encapsulated, so you cannot get to see to measure if this PT is still if any additional elongation or not, because at the end, I don't think it's not going to be an issue, because as I said, you get all the ducts grouted, and so the movement inside the ducts of this strand will be minimal, because you get full contact, and it cannot slice. I mean, it will not move this cable inside the PT system.
Hi, how did you prevent the corrosion of the strand? I've noticed you had some plastic ducts for the PT, but you still get corrosion between the joints unless it's a continuous plastic duct, and you also get corrosion at the beginning and the end, of the live end and the dead end.
Let me go to one of the pictures so it's easier. So this is between the joints. So in this case, when we have the segmenting compression, this is not going to get nothing is going to enter. Also, for this area, it will be fully grouted, as I said. All this area, when the cables are installed, we do the post-tensioning. This area will be fully grouted, and the only point that it can be damaged are the PT pockets. So
yes,
in that area, there is I don't know if I have a picture of that, but there is like a plastic cap that you put. I think there is one. Sorry, let me go here. Here, maybe here. No, it's not. No, I don't think there's going to be a. So at the end, you have all the steel, and then you have like a yes, here from the design point of view here. If I zoom in here, for example, let me try to make it as much as possible. Here, this is like a plastic cap that you put here, and when you fill all the system with the grout, the water cannot get into the.
Okay, and do you have any joints between the ducts, or is it one unique?
Only one
duct. Okay.
See, the strand go all the way around.
No, I'm talking about the duct. Is the duct a unique duct, or does it have joints?
There is one. The duct is continuous along the segment. Yeah.
Okay.
Yeah.
What kind of length was that?
Depending on the segments,
okay.
they were bespoke. The length was bespoke done for each of the segments, because even each duct for the same segment has different length because of the trapezoidal shape.
Is that why you use the plastic duct as opposed to galvanized?
The plastic duct we use it. We use it not for any purpose. It was as at the end the post-tensioning system supplier proposed that.
Okay.
And at the end, as it is embedded in the concrete, there is no risk of corrosion. Not because around it you have concrete, and internally you will have the grout when you fill all the system with grout. So at the end, it's plastic between concrete or grout all surrounded.
Okay, thank you.
Is there any other question? I have one. So if you had to start the design from scratch again, what would you do differently?
Well, before getting to details, I will try to ask an additional campaign to get the squeezing effect, a full knowledge of this effect, because I think this is the critical point of this project. The PT at the end is a structural thing. You know how much You need to stress to get forces. The concrete is what it is, so you know at the end, all the uncertainties and the hazards come from the geotechnical point of view in the tunneling. So try to get full understanding of the geotechnicals before starting to doing anything is the best thing. I will try to get in this project if I had to start from the beginning.
Because
especially the squeezing.
You had to do sensitivity analysis for
no, because at the end, when you are, this was a heartbeat project, so at the end the contractor and ourselves, we need to stick to the requirements. So the requirements give you jump from the bridge, you jump from the bridge. Because you need to challenge the client and say maybe your requirements are not as good as they should be, and this is a potential claim from the contractor or whatever. So at the end, everyone wants to follow the rules, and in this case it's better to challenge it and try to get confident that these hazards are within a low risk of happening.
Yep, that is.
Yeah, but at the end, don't forget that we are in Los Angeles, and the squeezing is one thing, but the major issue I think is when this type of fault will move by half a meter or more when that happens.
Hi.
Hi.
My question is the GI specific for the squeezing ground conditions that you said would be quite helpful to reduce the claims. What it consists of? Different.
In this case, I mean, there are I'm not fully aware what are the different geological campaigns that you need to do specifically for squeezing, but at the end, the target is try to get the low behavior of squeezing. So depending on the material that you have, all the boreholes and all the different geotechnical survey that you can do, at the end the target from the design point of view is try to get a low formula to see, depending on the relaxation of the ground and how bad is this ground, that to see how it relaxes, because at the end this strength deformation curves in this squeezing, maybe there could be a movement forever. It will get into an equilibrium. Hopefully at some point it will arrive, but that may give you a displacement that you cannot afford for the design point of view. But as I said, I will try to get what's the behavior of the ground and try to get this deformation, strengthening deformation curve to estimate how much we need to relax the ground to avoid, to be able to withstand the loads, the remaining loads with the segmental line.
Did you get the opportunity to optimize the alignment to try to reduce the demand on the segmental lining design?
You mean the alignment?
Yeah, the tunnel alignment.
In this case, the alignment was fixed. Well, it has a almost continuous slope upwards to the ocean, and in the horizontal point of view, we cannot change anything because it has to be on the public land, so it has to follow the main roads in order to avoid any issue with the neighborhood. So at the end, we were just following the main highways, and when there is a park, we could do it. We could cross it, and a golf as well. But any property or any building should not be on top of the tunnel to avoid an issue. This is more low issues in the US. So that's why, for example, for the existing tunnels, you saw that they were straight, so no one cares. No one was living there at that time, for sure. And nowadays, in order to avoid an issue, they prefer to follow the main road. That's why we cannot change.
Do you have anything to add on workmanship of the segments, i.e. cracking, obviously rejection of segments? Was there any increase with the additional?
For example, for the PT, we know that as you are doing so much segments, in some cases, the system, the duct was blocked. So what they managed is just to prepare like a tool with a screwdriver, with a flexible, that they put it in and try to remove some grout or some concrete material in order to get this block area free again. So they invented like the electric guys. So instead of putting the cables, they put like a drilling, a small equipment with flexible cable. They pull it in and they break the concrete and get that material, that duct free again, in order to be able to install the PT. And for the other segments, the most demanding thing, as I said, for the case segment in the squeezing, the second type, we saw that the radial pressure around the ring near the installation was so high that even with these two additional bolts to attach the key segments to the previous ring was not enough, because at the end the bolts have some tolerances, so there is a bit movement that it can happen, and it creates some offset in the longitudinal way if you cannot remain the segments, the key segments in place. So that's why they ended up with this additional tool, just to put additional restraints and make sure that that key segment is not going to move forward because of the radial pressure. So I don't know if I answered more your question.
There is only one more online. So they asked, during construction, how long after the placement of the ring was the stressing done?
It was, as I said, they built 3 additional countries in the backup system, and those countries were like at the 100 meters away from the TBM phase excavation, more or less. 100. They have like three countries, so they start pulling the cables like 100 meters, and in the next 30-40 meters they were doing all the stressing, grouting, and blocking, and everything. So yeah, from that 100 meters, far from the excavation point.
I think they are asking more like how long in time.
Time?
Yeah, since the segment is placed until it's.
Well, the segment you go with the TBM. You put that segment, the TBM continues. The trailing is following the TBM. When we reach that distance, they start doing it, and they have like, for example, they are doing like 6 rings, 7 rings per day, because at the beginning of that's the number I recall, 7-8 rings per day. So at the end, what they were doing, the whole PT should be done in less than 1 week. But at the end, this is not like a period of time, because as soon as they finish in one, they go in front in order to continue, because the TBM is moving. So they have some margin, because the TBM is not moving the whole time. There are some TBM maintenance programs, some stops because of cutting wheels, tools for replacement. So at the end, they play with these times that the machine is not moving, in order to try to match the production of the PT works with the TBM excavation.
Makes sense. No questions? Okay. So thank you very much for the presentation. I really enjoyed it.
Thanks to you.
Thank you.
To invite us.
Yes. Thank you. So I'm going to present quickly the next events that we are organizing. So we have the social next week, Thursday. It's at Regent's Park. It's going to be BTSYM in the park, and we will be playing some sports around. It's going to be sponsored by Becker, so join us. And yeah, we have the QR code on Google Maps just to find us in the park, because I wouldn't be able to find that cross in the park. So for the September workshop, it's going to be Maxam on drill and blast design for tunnels. So if you want to join, we are starting the organization of it, and we will open the registration. In case there are many people interested in coming, we may need to organize a different room, so we will try to open it soon. Next big event is the conference in London. It's going to be at the Arup office. This year the theme is Next Generation Tunneling, Innovation, Inclusion and Impact. And the applications for the abstracts are open, as well as for the sponsorship. So for this one, you just need to fill the form. It's a Google form, and submit the abstract, and then the presentation is the next step. So no papers are needed. It's quite easy, 5 minutes, and you can submit. And what has been happening? So we went, some of us from the committee, to the WTC. We presented what we've been doing with the other countries as well for the young members. Aya has come back to the committee, and she will be organizing the conference. And Hashmi has, he works for OTB, and he's joined to be the link with the BGA Early Careers Group. And yes, just for you to know that we have been engaging young members. The first presentation we had in January, there were 3 of them. One was online, and we are trying to make it happen. It's been a lot of work for all of us, but in the end, yeah, the committee is working in different things. I had an animation actually, because I did this for the WTC. So these are the different things we've been doing, and many more. So thank you all members of the committee, because we're working a lot. And another thing we did with the main BTS is the International Women's Day on the 6th of March, and we took some pictures that we are actually compiling now, and we have a live collage with pictures and quotes. So if you want to join, you just need to send your picture and your quote to the BTS, your members, and we will be updating this collage. So again, the presentation, we need abstracts and sponsors. And now the drinks will be sponsored by Sener, so thank you for coming on the presentation. So thank you very much. Yep.